The AI industry promised us an infinite, weightless digital brain, fueling the next step of human evolution. But if you look at the physical cooling infrastructure under a microscope, you find a glorified, highly temperamental radiator that is perpetually one sticky valve away from melting down. This is the anatomy of an industrial overheat. Every line of code we write, every model we train, has to go somewhere physical. It goes to massive, windowless concrete warehouses. They look like boring logistics hubs from the outside, but inside they are consuming massive amounts of power, specifically to run giant cooling loops. And right now, those cooling loops are hitting a physical limit. The chips are getting hotter, and our methods for cooling them are basically out of ideas. Let's look at the blueprint of how this system was actually supposed to work. At the center of this system is the chip, usually a high-density $80,000 processor that runs at about 85 degrees Celsius. To keep it from melting into a puddle of silicon, we use a heat sink, a block of copper that pulls the heat away from the core, but copper can only hold so much thermal energy. Eventually, you have to move that heat out of the building entirely. And that's where the water loops come in. Cold water is pumped directly to the rack where it absorbs the heat through a plate and travels back out as hot water. This hot water goes to a cooling tower where giant fans evaporate a small portion of it, cooling the rest of the liquid down to start the cycle all over again. On paper, this is a perfect, closed thermodynamic loop. It is clean, highly efficient, and predictable. But there's a catch. This entire multi-million-dollar cycle depends on a constant, uninterrupted flow. If the water pressure drops by even 10%, the heat exchange plate stops working. The heat immediately backs up into the copper sink and the chip temperature spikes. Within seconds, the processor reaches its limit. And at that point, the safety systems have to make a choice, either crash the entire model mid-training or let the hardware destroy itself. So to prevent this, facilities build layers of redundancy. Backup pumps, secondary loops, emergency valves. They build systems to monitor the system, and then they build systems to monitor those systems. It is an engineering marvel, and yet the core mechanism keeping all this together is essentially an industrial version of a radiator I once fixed on a 2004 Civic. Except this one costs $400 million and comes with a monthly software subscription. And just like that old Civic, it is incredibly sensitive to pressure. Which brings us to the reality of the stress test, because on paper, everything works. But in reality, AI workloads don't run in neat, predictable cycles. They spike instantly without warning. And when they do, the thermodynamic load completely overwhelms the baseline designs. This is where the math stops looking simple and starts looking incredibly expensive. Let's look at what happens when you push this system past its breaking point, because that's where the thermodynamic wall actually begins to fracture. This is where the corporate expectation crashes directly into the physical reality of the power grid. The investment thesis sounds simple. Acquire the land, fill it with next-generation chips, scale AI as fast as demand grows. The only problem is that the electrical grid doesn't read investor presentations. But in reality, a modern AI facility isn't just another building on the block. Because of the sheer volume of power needed to run those high-density chips and pump millions of gallons of water through their cooling systems, the largest planned AI campuses can demand up to a gigawatt of electricity. To put that in perspective, that is enough power to support roughly 750,000 homes. And they are trying to hook these massive thermodynamic sponges up to an electrical grid that was largely designed in the mid-20th century. Which brings us to a beautiful piece of operational absurdity. We are told we are living in the dawn of a hyper-advanced, clean energy future driven by artificial intelligence. And yet, because these data centers are demanding so much electricity so quickly just to keep their cooling fans from seizing up, utilities in several key tech regions have delayed the retirement of 50-year-old coal plants. It is a masterclass in modern corporate irony. We have built the most sophisticated digital intellect in human history, but to keep its radiator from exploding, we are forced to burn crushed black rocks from the ground like it's 1890. The data cooling economy isn't a tech market, it's a land grab for raw power. If a data center cannot secure a massive, dedicated pipeline of electricity from the local utility, those state-of-the-art server racks are nothing more than incredibly expensive, beautifully engineered paperweights. And the utility companies are starting to push back. They are looking at the sheer volume of juice these cooling loops require, looking at their aging transmission lines, and realizing the math simply doesn't add up. The real disaster happens when the AI actually starts working, because when a model begins a heavy training run, that power demand doesn't rise slowly. It hits the system like a physical hammer. To understand why this system fractures, you have to look at how an AI model actually consumes energy. When you stream a high-definition movie, the server hosting it runs at a relatively steady, predictable pace. The cooling system can cruise on autopilot, but training an AI model is not a steady process. It is a sequence of violent, instantaneous spikes. When a training run begins, thousands of high-density GPUs transition from near-idle to 100% capacity in a matter of milliseconds. In the world of electrical engineering, this is known as a transient load spike, and to the physical infrastructure, it behaves exactly like a hammer. On the electrical side, this sudden demand draws a massive surge of current through the local substation. If the grid's frequency drops by even a fraction of a hertz because of this sudden pull, safety relays are programmed to trip instantly to prevent a widespread blackout. But let's assume the substation holds. The power gets through to the server room. Now the hammer hits the liquid cooling loop. Because those thousands of chips heat up almost instantly, the temperature of the silicon spikes to 85 degrees Celsius in less than a second. Under standard thermodynamic designs, the copper heat sinks are supposed to absorb this initial shock and transfer it to the water loops. But water has mass, it has inertia. If heat begins entering the cooling system faster than the cooling system can carry it away, a localized thermal bottleneck develops. The heat literally piles up at the copper interface faster than the water can sweep it out. Which brings us to the breaking point. Most modern AI data centers rely on single-phase liquid cooling, meaning the fluid is designed to stay strictly liquid. But when the heat backs up past the system's physical limits, it forces an abnormal, catastrophic failure state. The liquid directly touching the microchannels of the copper plate begins to vaporize. Tiny bubbles of steam form on the surface of the copper. Because steam is an incredibly poor conductor of heat compared to liquid water, those micro bubbles act like a thermal blanket. They insulate the chip, trapping the heat inside. This is the point of critical heat flux. Once this blanket forms, the temperature of the silicon rises exponentially. In a fraction of a second, the chip reaches its thermal junction limit. At this exact moment, the automated safety systems have to make a choice. They can throttle the processor's speed, which doesn't corrupt the data, but it drastically slows down computation, dragging out training times and burning through millions of dollars in wasted energy and least time. Or, to prevent the hardware from literally destroying itself, the safety systems trigger a hard, emergency shutdown. The power is cut instantly, and the entire training run crashes to a dead stop. And this is the ultimate irony of the data cooling economy. We are building increasingly complex neural networks to solve humanity's most complex problems, but the entire system is physically bottlenecked by the speed at which we can push water across a tiny piece of hot copper. We aren't fighting a software limitation, we are fighting the laws of thermodynamics. And right now, physics is winning. With the cooling loop officially dead on the table, it's time for the autopsy. The training run collapsed because the cooling system reached critical heat flux, but blaming steam bubbles is like blaming gravity for a plane crash. It's a symptom, not the root cause. The failure actually began years earlier when AI computing outpaced the physical infrastructure built to support it. To meet the sudden surge in demand, operators had to retrofit legacy air-cooled data centers, packing them with high-density chips pulling 10 times the power. It is a fundamental mismatch, running a high-performance racing engine inside a standard family sedan. So why haven't we solved this yet? The first instinct was to push air cooling to its absolute limit, blasting massive industrial fans to force cold air through legacy server aisles. But air has a very low thermal capacity. Once chip density crosses a certain threshold, the physics of convection simply run out. That forced engineers to look at liquids. Water is an excellent coolant, but unlike dielectric fluids, it carries a massive electrical risk. Because industrial cooling water inevitably contains dissolved ions, one microscopic leak from a copper plate will instantly short-circuit a multi-million-dollar server rack. To eliminate this risk entirely, the industry has been forced to explore alternative fluids. One increasingly important approach is immersion cooling, using dielectric fluids, synthetic oils that do not conduct electricity. Instead of routing liquid through complex plumbing, the entire server rack is submerged directly in a bath of this oil. In this immersion cooling system, the fluid boils off the chip, rises to a condenser plate as gas, and drips back down as liquid to repeat the cycle. Physically, it is a brilliant thermodynamic solution. Operationally, it is a nightmare. If a single card fails, a technician can't just slide it out. They have to put on heavy-duty gear, hoist a dripping 70-pound slab of silicon out of the oil, and let it drip dry before touching a single screw. It slows maintenance to a crawl. And in the data economy, every minute of downtime costs tens of thousands of dollars in lost compute. The autopsy leaves us with a stark conclusion. The hardware is too fast for our plumbing, and our plumbing is too slow for our code. Which means we are running out of runway. When a system runs out of runway, there are no easy pivots. We cannot engineer our way out of the laws of thermodynamics. You can build larger cooling towers, invent better synthetic oils, and design highly advanced microchannels. But all you are doing is moving the heat from one place to another. You are not destroying it. You are just paying to push it around. And that is the quiet truth of the modern cloud. We treat the digital world as weightless, infinite, and clean. But the physical footprint of that intelligence is heavy, finite, and increasingly dirty. The ultimate bottleneck of artificial intelligence isn't data. It isn't algorithmic complexity. It is how fast we can pull heat out of silicon and how much power we are willing to burn to do it. If we want to keep scaling this digital brain, the infrastructure has to change fundamentally. We may see more data centers built alongside dedicated sources of reliable power, including nuclear energy. We will have to treat computing power not as a utility, but as a precious, heavily rationed physical resource. Until then, we are running on borrowed time. We have built a mind that can rewrite human history, but it is still entirely chained to the earth. And right now, the chains are starting to heat up. This is the physical blueprint of the data center cooling economy. And the heat is rising.